The speaker, Mike Wolf, from Rice University, courtesy to the Simon Stanford. And his title is Towards the Boundaries, Towards Thurston Boundaries of Higher Rank Teichmüller Space.
Thank you. Thank you very much. Thank you, Leon. Thanks for the invitation. It's a great surprise. So maybe I'll step out of character before I begin and say what it is. Maybe just to explain some of the choices I might make. So I gave a talk on Tuesday in the workshop, so I want to give a talk that's a colloquium. On the other hand, I have workshop participants here, so the talk should be self-contained because it's a colloquium. It should be different than the Tuesday seminar, and it should still be appropriate for the workshop. And I'm not any deeper than I was a week ago. So, sorry? Yeah.
Should exist a unique talk satisfying whole.
No, there should exist at most one good talk. Okay, so I will make some funny choices through here to try to keep those constraints. Okay, let me start. So the talk is about surfaces. So throughout the talk, so S is a surface of genus G at least 2, and on which, so it's a differentiable surface, so closed surface differentiable, on which we place various geometric structures from time to time. Ways of measuring angle, ways of measuring distance, other sorts of things like that. And I'm interested in studying the character variety, or some components of the character variety of representations of the fundamental group of this surface into some Lie group up to conjugation by elements of the Lie group. So. And so I have in mind, and so really the organization of the talk is just to go through some of my favorite groups until I run out of time. And they're all going to be low-dimensional groups. So I have a few specific groups in mind. No reason to be mysterious, so I'll talk about PSL2R, or discrete faithful representations in PSL2R, the classical Teichmüller space. Once I know that, then I'll talk about PSL2R squared, or cross PSL2R. Briefly, I will not be able to say anything about PSL2R cross PSL2R with 3 factors, and I'll say why, so this won't happen. Let's see, I won't talk about PSL2C because that was Tuesday. But I will then talk about, I will talk of a number of the interesting sort of phenomena that we can really start to see in PSL3R. And so for this, I'll give sort of an incomplete discussion and say where I am and maybe where I can't go. And then I will not have time to talk about SP4R, though I will probably try to plug my postdoc who's working on it. Okay, so that's sort of the plan. And so what am I interested in doing? Let's see. Oh, for the conference participants, secretly I'm always talking about solutions to the Hitchin system for Higgs bundles. And that's probably the last time I'll use the H word. So, so let me start. Let's see, make sure I say all this. And so my plan is, so I'm interested to specialize further in asymptotics of one of these components, and I'm interested in approach. To the approach is analytic. So in some sense, rather than synthetic. Let's see, and there's an extra constraint. Right, and so making it analytic, so this does give some contact with the Higgs bundle point of view, so it's an extra constraint, but I think it actually sort of one gets a little more more of an understanding about Higgs bundles along the way. Okay, so that's just a throwaway remark. So let's just start with examples of what I have in mind. So the most basic example, and so the model case is discrete, so G is PSL2R. So if you like, sort of isometries of hyperbolic 2 space. And so I'm interested in surface group representations into PSL2R. This is, so let me write that. So I'm interested in and I'm going to say discrete and faithful, pi 1 of S into PSL2R. Repeating myself, but I want to up to PSL2R. So a particular component. This is the same as when I take that component as the classical Teichmüller space. Another way of thinking about Teichmüller space is one looks at hyperbolic structures on this differentiable surface. So I'm interested in all the various hyperbolic metrics that I can put on this closed surface. There's a lot of them. And I want to distinguish between a hyperbolic metric on the surface and one I might get by taking that hyperbolic metric, taking a very small diffeomorphism and pushing my hyperbolic metric by that small diffeomorphism. So one mods out by this sort of equivalence under isotopy, and it's just well known that this is some ball of dimension 6g minus 6 after you do that equivalence. Okay? That's a basic example. I said I was interested in asymptotics, if you like, in degeneration. So here's my Teichmüller space of all the hyperbolic metrics. And so I'm interested in what happens as I leave all compact sets. How does one compactify this Teichmüller space in an intelligent and useful way? Let me steal my own drama. So I'm going to describe for you in the beginning an analytic approach to what's famously called the Thurston Compactification, which saw great success in the 1970s for classifying and explaining the diffeomorphisms of a surface. But it's a colloquium. Let me just talk about degeneration a bit. So if I have a surface, there are a couple of ways. How does one imagine degenerating in the Teichmüller space? Well, when I was a graduate student, Halsey Royden explained this to me in terms of ways of murdering the surface. We're in gentler times, so one can. I changed my mind. So one can pinch off this neck. That's one way of destroying the surface. Another way of destroying the surface is to take the neck and twist it a lot. Just keep twisting and twisting and twisting. And then the third way would be pinch a bit, twist a bit, pinch a bit, twist a bit. I'll leave it to your imagination how to articulate that. All right, so that's ways to leave all compacta in the space of hyperbolic metrics. Okay, so as a model, here's the approach I want to take. So here I have some family. Let's give it a name. So I have metric, say, rho sub t. T is going to infinity. And I don't know what to put here on the boundary. Some sort of infinite object. I don't know. Some sort of infinite object. So the approach I'm going to take is a little odd. So I'll fix some particular surface, S, and I only really care that it's a Riemann surface. So S with the conformal coordinates of some particular point in this Teichmüller space, right there. And I'm going to compare the family of metrics leaving all compact sets with that one, with that surface. So I'll compare rho t to x. How do I do that? Well, I'll imagine a map from this Riemann surface to this hyperbolic surface, homotopy class of the identity. And I want a best map. In this setting, the best map has least energy. So the integral of du squared, properly understood, is the integral of grad u squared will be the energy. I'll minimize that. These things exist. They're unique. They're nice. Let's see. So this is a functional. So the only important thing to say about this functional is that this functional has the right invariance. So it's a conformal invariant on x, and it's a metric invariant on my target rho t. Okay, so I can use. So I'm on a Riemann surface. I can do complex analysis on the domain. I'll get complex analytic objects here. But I'll be able to probe the hyperbolic geometry there, or if you like, be able to probe the resulting representation that comes from the holonomy of that hyperbolic metric. Okay. Great. And of course, there's I said I'm minimizing energy, so of course there is an Euler-Lagrange equation. I think the only time I'll say anything that's really at all PDE-ish will be towards the end if I get there. But the quality of the advantage of having a conformal invariant is that once one has an Euler-Lagrange equation for a functional that only depends on a complex structure, complex analytic objects emerge. Okay? So you might think about it, if I had a flat target, so e.g., so one gets holomorphic objects. This is just sort of a theme in geometry. Comment on that in a moment after I finish this, after I make to continue with this theme a bit. So, for example, if I had a flat target, then my Euler-Lagrange equation would look something like, Laplacian u equals 0. I'm minimizing energy, so the Euler-Lagrange for energy is Laplacian. I'm on a Riemann surface, so on the Riemann surface, I can think of Laplacian as d bar of du. So what that expresses, associating properly. So this is going to say that round du is holomorphic. Locally, and maybe you want to think of this more geometrically as I look at the tangent map for u, and I look at its 1,0 part, and that's holomorphic. Or there's many ways of saying this. I could pull back, this metric on whatever my flat target is, and then look at its. In this case, it's it's one. Now I've got myself. I'll pull back the line element, and I'll take a look at the 1,0 part. So there's a number of ways where I get something that's sort of holomorphic, and that becomes a theme for conformally invariant functionals, which we'll see in a couple more instances. And so this, I guess, so one is used to this sort of development as, one can, for instance, one can look at the, algebraically, one could look at the cohomology, and into the cohomology, one might look at differential forms, the sort of de Rham theory. From the differential forms, one could pick out, just very quickly, a harmonic form. And just as sort of a Hodge point of view. And then so do something holomorphic. From this, extract a holomorphic form for a sort of, as one would, I don't know if I want to use B. Grand and say Dolbeau, but this theme of algebra to differential topology to something, to an extremal problem in differential topology is something holomorphic is, has broad extent throughout geometry. So this is just one sort of example. Okay. Great. So I'm interested in these harmonic maps, and I don't want to start putting differential equations on the board. How to think about harmonic maps? So I want to do a series of examples. For my Tuesday participants, very few are the same, but the first one is. So the first example is I'm interested, so let's find a harmonic map, just one. And so I want to find a harmonic map from a Riemann surface, the plane, to a Romanian manifold, hyperbolic space. And so what should that look like? Well, so here's the plane, and I'll start with a coordinate z, and z is x plus iy. And I'm not, so I don't know much about harmonic maps, so I'll just map this from z to x. So I'm mapping down here to the real line. And if anything's harmonic, z to x is harmonic. Take the real part of a complex coordinate that's harmonic. Map this to hyperbolic space by some isometry to a geodesic. The gamma of x for this is a geodesic. And something harmonic followed by something which is metric preserving should be harmonic. So this is harmonic. So the relevant holomorphic object is called the Hop differential. From Hop, who used it in investigating surfaces of constant mean curvature. And it's just what I wrote over there, in some sense. So one pulls back, formally as a definition, the metric on hyperbolic space, and looks at the 2-0 part, and calls that Q, and the harmonicity of the map forces this to be holomorphic. So this is holomorphic. It's not a holomorphic one differential. It's a holomorphic quadratic differential. So it might be written as a section of this. If I call, I chose in this case. So in general, if I have a Riemann surface, it will be a section of the canonical bundle squared on the Riemann surface. So it's a dz squared object. So somehow it looks like locally some phi of z dz squared, where this is holomorphic. Okay, but it's pretty obvious what it should be, because if I take the complex plane and I translate up or down. If I translate down, I don't change the map. If I translate over, I really don't change the map. I'm just going to sort of translate along the geodesic, which has where I have a translation group of isometries anyway. So this, whatever this differential is, it should be invariant under translations, both up and down. So, so in this case, Q is dz squared. So it's the number 1. So that phi function is just a constant, and so that's what it is analytically. Geometrically, we can understand what it says. So, so the square root of Q is dz. Great. That's a little easier to think of. And dz has a direction where it's real and a direction where it's imaginary. So the picture that comes that is perhaps the only picture that we really need is that, and I promise to be finished with the example of z goes to x really, really soon, is that on C we have the directions where the square root of Q is real, and those directions get mapped to the direction of maximal stretch of the map, and we have the directions where the square root of Q is imaginary, and these are collapsed under our map. So in this y direction, I have the preimage of a point, and that preimage just goes to a point here, and so these are the directions of minimal stretch. So the holomorphic object, when you think about these sort of natural directions of real and imaginary part, captures the differential topology of the map. Okay, so let's solve our asymptotic problem in a very simple case. So, so the simple case of the asymptotic problem is this. Just armed with this example, we can imagine a boundary value problem. So here, my original surface, my fixed surface, SZ is some fixed cylinder. Maybe I'll put the lengths to be 1. And I want to map to an extreme hyperbolic cylinder, something nearly degenerate. What does that look like? Well, it's going to have a very skinny neck, something like that. And so, so you're a harmonic map, and I have no colored chalk. What happened to my colored chalk? Oh well. Thank you, Aaron. It was there earlier. Okay, I appreciate it. So, so what do you do? So the basic geometry is that if this is size epsilon, then that's much longer. So this is size roughly log 1 over epsilon. So in any sort of, and I'll fix the boundary value, so that's not an issue. And so in any, so if I want to minimize energy, there's not a lot of energy coming from having to stretch vertically. I mean, in fact, I'll save a little bit. The core curve going to the little one, the little epsilon curve, will have energy like an epsilon squared around there. The major amount of energy comes from stretching longitudinally. So if I think about, maybe I'll just draw curves that are equally spaced here. Some of them will crowd a bit into the center, because if they crowd into the center, they can save a little bit of energy by not having to stretch too much up and down. But in general, since the most amount of energy is coming from the longitudinal stretch, they'll stretch them, they'll be more or less equally spaced. So equally spaced curves here go to equally spaced curves there. And the moral of the story is that, once again, this top differential is dz squared, but we learn even a little bit more from this quadratic differential, in that if I want to know the length of an arc, say from here to here, that length gets predicted by looking at its preimage and counting how many lines we cross. Okay? So this length is predicted by this sort of intersection number with the vertical, with the minimal stretch foliation. So armed with that, great. So this tells us the answer, or gives us a good clue about the answer for PSL2R, because so we get a quick sort of geometric or sort of Thomas, well, I don't know, numerical explanation of what the answer is, and then I'll go back and I want to fill in a little more geometrically. So so this gives an answer, one answer for this Teichmüller space compactification, take some boundary. And so in other words, the picture is this. One has these families going out to infinity here, and I have an x. And these all will have some length spectrum. And if you keep track of if you keep track of which curves have which length, so I'm sort of imagining an ordered length spectrum. I have gamma 1's length and gamma 2's length, etc., rather than just the collection of numbers. If this family is going to leave all compacta, some length is getting big. How do I track which lengths are getting big? Well, they can get tracked by looking at these Hopf differentials of this map. So the point is the length spectrum is predicted by intersection numbers, by intersections with the Hopf differentials of the harmonic maps. And so that sort of so the object I could put here is now, in fact, it becomes, this is an observation of Thurston, is that it's enough to keep track only of the projective length spectrum, divide out by some large one. And so what do I put here? Some sort of, some version of minimal stretch foliation. And normalized because I'm only interested in projective stuff. So the normalized minimal stretch foliation of Hopf differentials.
Why couldn't you leave all compacted by having all the lengths go to 0?
That doesn't work for hyperbolic surfaces. Yeah, simple reason is here. If I start making one of these go to 0, then the ones that come across get very, very long. Okay. Great. Great. So So the feature I want to point out here is that we did something which I remarked on Tuesday. My training tells me not to do. So I'm interested, I was interested in studying a component of space of representations. Interested in studying algebra. What was the first thing I did? I froze some Riemann surface somewhere. I said, that's how I'm going to begin. Well, then everything I do somehow depends on the Riemann surface. So it's not natural. When people do Riemann surfaces, why study Teichmüller spaces? Because the algebraic geometers are studying the natural Riemann's moduli space of curves, and that's the natural object. This is the only way the analyst can compete, but this is sort of a poor cousin. So one wants only objects that will descend to moduli space, or be mapping class group invariant, and when I fix the X, it isn't. But when I put on these sort of topological objects at infinity to Teichmüller space, these objects at infinity are mapping class group invariant, which I guess I should define. So mapping class group, which is there's all the diffeomorphisms on the surface, modulo those that are isotopic to the identity. So these are mapping class group invariant. So the entire Teichmüller space then is mapping class group invariant, and so that's very useful, as Thurston showed. I want to do better and to introduce. So I want to have something else out here at infinity that's more geometric. So this comes to my third example of a harmonic map. And this is, in some sense, my final overlap with Tuesday, for those keeping track. So I showed you a map whose Hopf differential was 1 times dz squared. So if I think complex analytically, and I think about increasing the complexity of my example, the next step in increasing is to increase the complexity of the Hopf differential. So I'm going to turn things around. Instead of making domain or range more complicated, I'm going to make the Hopf differential more complicated. So I'll still try to think about what's a map from the complex plane to H2, which are the simplest sort of domains and targets I could think of. But I'll say, what is it if Q looks like, say, z cubed dz squared. Just some polynomial times dz squared. I'll up it a little bit. Well, of course, this now has a 0. I now have some distinguished point. And if I take, trust me, if I take the square root of q and I start looking where it's real and imaginary, I get some picture that looks like this. There's a few arcs in some directions that head out from the 0, and then there are these other shapes. I'm going to draw the parts where it's real, or if you like, if I look at the square, so I'll look at where q on vectors is positive. And I get something that looks like this. And then there's the negative ones, the other foliation. So this is the maximal stretch foliation I'm drawing, where it's going to stretch the most. The minimal stretch will be orthogonal. And so what's this harmonic map? Well, the point is that, again, the plane is a big place, and you're a harmonic map. So if I'm, for a point that's very far away from the 0, when that point looks around, it doesn't see a 0, and so it thinks that it is this example. It thinks the Hopf differential is dz squared, so it imagines, so what should the map be? Well, it should be very close to to that map for dz squared to be very close to taking these leaves and mapping them to a geodesic. So the image here up in the plane is that these leaves become very close to a geodesic. These leaves up here become very close to a geodesic. These over here become close to a geodesic, etc. And so the image of the plane here is some regular ideal pentagon. Now, okay.
Is anything mapping to Pentagon?
I'm sorry?
Is anything mapping to the Pentagon?
Yes, so the entire complex plane maps into the pentagon. And so this leaf here is going to go to some curve that's very, very close to that leaf. Okay. The one thing that I did very fast, and we'll come back to, is, certainly these leaves go close to here. I told you these leaves went close to here. So something happens around there where I flip solutions from this geodesic being a solution to the harmonic map problem to that geodesic being a solution to the harmonic map problem. So I'll talk more about, that's some version of like what might be called a Stokes phenomenon. The Stokes phenomenon is an actual math word that refers to behavior of solutions to ODEs at regular singular points. This is not an ODE, but it's phenomenologically very close. So I'll talk more about that later. But so, store that up.
Is the energy density? It is very strong at the vertex, at the zero?
No, it's not that strong. Actually, I'll make a comment at the end, which might be around 7:30, but about that. So, no, there's more out here actually, in some sense. So now I want to go to start thinking about so with these examples in mind, I told you that I was interested in closed surfaces, so let me go back to closed surfaces. And I told you we're interested in this setting of PSL2R about looking at these holomorphic quadratic differentials. And in particular, their foliation structures, these sort of directions where they're positive and directions where they're negative, like the directions where locally the square root is real or the square root is imaginary. On a closed surface, these have substantial dynamics. So sort of confusing dynamics. I might have some zeros, and then these set out, and then they wander around, and then they come back, and I'm going to end up in trouble. And so they sort of wander all over the place. Anyway, they wander all over the place. It's somewhat confusing. It's a little easier to lift to the, so if this is S, we can draw the picture up on the universal cover. Well, in the universal cover, of course, I still have these zeros, and well, we draw a few of them. But as this leaf wanders around the surface, it comes very close, maybe back to itself. And so maybe so I follow this leaf, and so way up here, I see a copy of the zero again. So so these dynamics. So I'm sorry. So this leaf space is complicated, and leaves will come very, very close to singularities if you wait long enough. Okay. So what we can do is, so I want to try to understand the leaf space. So let me just project to the leaf space. So every leaf goes to a point. So here I have a bunch of leaves, so they'll go to a segment. That's part of the leaf, so it'll have a vertex. This leaf, I have leaves going through here, so I have a vertex there. Here's another vertex. But way up here, very close to this vertex in the universal cover, is another vertex. And in fact, because of the sort of chaotic winding behavior of these trajectories, where a typical trajectory comes arbitrarily close to a countable number of vertices, this tree, which it is, has typically a dense set of vertices. It's typically locally infinite, and it's because the distances between the points in the tree, which I could explain how to measure, since they typically take values only in real numbers rather than, say, like the integers, which you might be used to for trees that keep track of combinatorial group theory. So this is called an R tree. And let me point out one more thing. This map from this universal cover with these trajectories down to this singular object, this real tree, it has the form in the correct coordinates of z, x plus iy, once again going to x. So this map from the universal cover down to the real tree, so this map is harmonic and equivariant. And it has, if this is the lift if this is a picture of Q tilde, then it's harmonic, and the Hopf differential is once again Q tilde, because it's just z goes to x. It's the same example we started with.
Equivariant with group? Or?
Yes, equivariant with respect to this surface. Okay. I can't resist one example. I'll probably regret this, but just to sort of slow down the discussion a little bit about harmonic maps to real trees. Everyone in the room is actually familiar with harmonic maps to real trees. Because here's an example, my favorite examples of harmonic map to a real tree. I have them. So be the map from C to R, where I'll take x, y, and send that to x squared minus y squared. Call that u. And so what is that map? Well, so let's draw the level sets. Here's where the map is 0. So here's u equals 0. Over here, u is positive. Over here, u is negative, positive, negative. So if I map to the leaf space of this, of C, then the leaf space, so I have a half line for that side. I have a half line for the neighborhood of the positive y-axis, half line. So here's where it's positive. Here's where it's already labeled, negative. Here's where it's positive. So that's maps to a tree. And what is the operation to get to R? It's an isometric folding of the tree branched at a point. So we identify positive, and we get positive, and so this gets folded together, this gets folded together, and that is the z goes to z squared. Z goes to real part of z squared that is too elementary to get mentioned in a complex analysis class. But somehow I didn't understand it until I started folding trees. I don't know. Okay, and I do regret that. Okay, so Okay, so let me return to this PSL2R case. Here's a fact. So here's Teichmüller space again. Still in PSL2R. I hope to get out of it soon. Here's my base Riemann surface, SZ. A fact that was one of the elementary facts in Hitchin in '87. I did something on this, which is not so important, is that if one looks at the quadratic differentials, so one looks at this space of holomorphic tensors on X, then to each row T in the Teichmüller space, to each possible target, there's some unique QT tensor back on X, which is a Hopf differential. So there's some version of exponential map that actually just happens. If you have a straight line, some ray, say TQ infinity in the vector space, this becomes some family of metrics, rho T, determined out in Teichmüller space. Okay? I'm still interested in what happens here. Well, here's the picture we have with all the examples. That clock's right? Oh dear. Shoot. Here's the picture. I drew. I take a Q like this, and I'll think about TQ. As for large T, for these neighborhoods here and here and here start to get isolated. They're far away from each other if I take T times Q. So what does the harmonic map look like? So the image is something, I sort of see an ideal triangle around here. I'll see an ideal square around there. I'll see an ideal triangle down here. I told you I was interested in projective stuff. So if I divide by T, then these get to be very close together. This distances start to shrink. These all become geodesics because this is through here. Through here I have just plain old dz squared. My very first example, they become geodesics. So this ideal square starts to shrink, and then I can put in the ideal triangle over here somewhere, which I can't really do well. I'm getting lost. But very small. And if I let T go to infinity, what one gets is that Y, that ideal triangle becomes a Y, that ideal square becomes an X, and the ideal triangle sticking off of it is another Y. So what is the image? So this image is a real tree. And so what one sees is that at the, if I take this X with this ray, then TQ, then the family associated to that is the R tree corresponding to Q. And these harmonic maps to the surfaces converge, the harmonic maps to rho t converge to the harmonic maps to the real tree. So in some sense, the geometric object to associate at infinity is a real tree that is predicted by this quadratic differential there. And these, okay.
Is this different from the previous compactification?
It's the same. I just put a geometric object. A different interpretation. Sort of the previous previous way I described it was in terms of accounting. Let's keep track of lengths. Now I want to actually have some geometric object at infinity. The accounting is the same. If you want to know lengths, just take a look at the path in here, measure it. But it suggests that what we want to look at for asymptotics of these representations is some sort of geometric object, some sort of singular object that one might attach at infinity. Okay, next example. So example 2. So here I'm imagining that I have so my representation is is a representation in the PSL2R. So I have a row 1 and a row 2. This is my element of pi 1s into this group. Well, so how does one compactify this? It turns out, there's a fact, that there's a unique, so let's think about H2 mod row 1, I'll call that x1, and H2 mod row 2, I'll call that x2, and I'm looking at the product of x1 cross x2. So in x1 cross x2, it turns out there's a unique minimal surface. I don't know, y. So I have, my picture is I have x1, I have x2, and somewhere there's a graph over each of them called y. There's a minimal surface. This is originally due to Rick Shane. So how do we compactify this? Well, so I might imagine at this point, maybe I have a family x1t. It's heading over here to a tree. And I have this other family x2t. It's heading over here to a tree. And what can you get as a limit? So what this happens here? Well, so this is work of my student, sort of in progress. And so one gets, so it depends on the trees. It depends a little bit on the rates you approach, but mostly it depends on the trees. And these trees can have portions that came from foliations that intersected each other, or it comes from portions that are parallel. So if the trees, so I'll just say, if T1 is somehow transverse to T2, and we won't have time to really get into that, but you can imagine the foliations are transverse, then this minimal surface, yt, some sort of midpoint here, then yt goes to some sort of like product of the trees. So it's some sort of flat, two-dimensional singular object. And the uniqueness Yeah. So, in fact, what we're saying about PSL2R cross PSL2R is we can, for every one of these pairs, there's some unique minimal surface y, and that minimal surface y sits in a whole bunch of pairs. So down here I might have Teichmüller space. And what I just told you is, suppose the y's sort of wander on up, and they wander on up to a T1 cross T2. That's fine. And so I get this flat singular thing. I want to point out something. The other thing the y's can do, let's just do it as an example, is that maybe x1 just sits there, and x2t goes to a tree. So in that case, so in this case, the limit is a tree. But then, of course, I have like buildings in one direction, trees in the other. So there's these directions where one gets a limit which is some sort of hybrid object, which is partially a building, so two-dimensional, and partially a tree, and that can be somewhat predicted from the pair of trees. Okay, that's sort of interesting. Now, let's skip a bunch because I'm running very late. We started late. So the next example is SL3R. So this is higher rank. So was SL2 cross SL2, but somehow this feels like a more natural example. Everything I'm going to say is joint work with Dumas. The midpoint is one can look at good work of Gabriele Mondello, Francesco Bonsante, and Jean-Marc Schwenker for lots of details there. So in this case, the variational problem is different. I had started with harmonic maps, minimal surfaces. In this case, we're still interested in harmonic maps from lift of a Riemann surface into a symmetric space, like I was in previously. The SL2 mod SO2 was hyperbolic space. So now I'm interested in upping the dimension a bit. But these maps arise as Gauss images of a different variational problem of what are so-called affine spheres, which were popular around in time of Blaschke, et cetera, in the 1920s. And the picture is this, that the particular component I'm interested in, these representations, so the component, so the Hom I1S SL3R, this particular component I care about, by work of Choi and Goldman, are what are called convex, can be identified with convex RP2 structures. By which I mean that if one starts with the universal cover and maps it into RP2, when the developed image is some convex domain. So this is dev of S tilde in this setting. Over this domain, there's one can look at the cone, And I'm interested in radial graphs over this cone. I'll just say, so it turns out in this setting there's a unique what's called affine sphere. Affine geometry. So what's an affine sphere in words? It's a variational problem. For a smooth affine sphere, one looks at the osculating ellipsoid, best osculating ellipsoid at a point. The best osculating ellipsoid at a point has it has a vector supporting it from the center of the ellipsoid. We have ellipsoids everywhere, and every one of those vectors meets at the distinguished point. Very rigid. It's a sphere. All the normals meet at a point. And that's, I've told you what an affine normal is slightly. Oh gosh. Shoot, how am I going to do this? I can't do this. I can't do this. That clock's right? Okay. Okay. I'm going to say something. To these things, one has, again, associated to this affine sphere, there are holomorphic objects, so x, kx cubed. So I'm interested in cubic differentials. I'll say it this way. I told you what dz squared was, dz cubed. So here the analog of geodesics are so-called Teichmüller surfaces. They are in the convex RP2. In RP2, these are graphs over a triangle. If I were to draw this in space, this would be the graph x1, x2, x3 equals 1. And the interesting thing about it's what I want to point out about these is that they have they're the image of a plane to this, and so when if I map this to there, the mapping, which I could write as real z, e real z, e real zeta z, e real zeta squared z, is not homogeneous in the space. I think I can't do this. I can't. I want to get to the Stokes phenomenon. I can't get to Stokes phenomenon. I think I better just give up. There's an analog for SL3 to what I did for SL2. Better part of valor is just to quit. I'm very sorry. So.
Questions? I have a question. Do you have some differential equations related to this? Like
yes.
Schwarz and for SL2, here it should be like a higher order analog of Schwarz and derivatives.
Yeah, there are Schwarzians here. So I said SL3R. One can look at SL3C. In SL3C, there are these objects that I'm not very expert on, that there's been some discussion in the conference about, called OPERs. There's a couple of interpretations of those. So one can look at differential equations that look something like y triple prime plus, say, ay prime plus by equals 0, where this would be a quadratic differential and that would be a cubic differential. I'm lying a bit. And one can look at the monodromy and study that. And one can actually, and so there's interesting things where you try to, say, study what happens in asymptotics of this.
Other questions? If not, let's end this quickly.